Welcome back. In this video, we're going to talk about linear systems. So recall from the start of the very first video that a linear system had m equations and n unknowns and took this form like this, where you've got the unknowns, the x's, the coefficients, the a, and the right-hand sides, the b's. So what we're going to observe is that we can rewrite this in terms of matrix vector multiplication simply as ax equals b, where A is an m by n matrix, B is going to be a vector of length m, and X is going to be a vector of length n. And notably, if you just expand all of this out, you'll note that this notation here, if you use the definition of matrix multiplication, well, the top row, what you'll get is you'll get A11 times x1 plus A12 times x2 plus A13 times x3, and so forth, all the way up to A1n plus xn. And that'll be the first component, which has to be equal to the first component over here. So you'll have the equation from the previous version of the slide. We're also going to recall that AX is going to be a linear combination of the columns of A. And this leads us to an insight. The only way that there will be a solution to AX equals B is if B can be written as a linear combination of the columns of A. That is, if B is an element of the column space of A. In general, there are three possibilities. There could be an infinite number of solutions to AX equals B. There could be one unique solution to the linear system, or sometimes there's unfortunately not any solutions at all. In the case of 1 and 2, then B will be an element of the column space of A, but in case 3, B will not. It's also going to be useful to talk about special types of matrices. A matrix D is called diagonal if there's non-zero entries here on the main diagonal, but all of the other entries are going to be zero. So in general, there's going to be n squared matrices or n squared entries in this matrix, but all of them except for the n on the diagonal are all assumed to be zero. And there's actually this very special choice of diagonal matrices where all of those diagonal entries are called 1. This matrix is called the identity matrix, and it has the property that I times A is equal to A times I is equal to A for any n by n matrix A. In other words, it can be thought of as the matrix version of the number 1 because multiplication by it doesn't do anything. Some other relevant special cases is a lower triangular matrix where all of the entries on the above the main diagonal are 0. So the lower triangle has the non-zero entries. Similarly, there's an upper triangular matrix where everything below the main diagonal is going to be 0. Some other useful classes are symmetric matrices. That's when Aij is equal to Aji. Hermitian is also sometimes called conjugate symmetric. So Aij is going to be the complex conjugate of Aji, where again, this star here is denoting the conjugate transpose. And there's also skew symmetric / anti-symmetric if Aij is negative Aji. And then similarly, there's skew Hermitian or anti-Hermitian where Aij is negative Aji. Up next is the inverse of a matrix. If there is some matrix B such that A times B is equal to the identity and B times A is equal to the identity, then B is called the inverse of A, and it's written as A to the negative 1. If this inverse exists, then A is called non-singular. Otherwise, it's called singular. We note that if A is a square non-singular matrix, then we can always solve AX equals B by writing X is equal to A inverse B. And in theory, this always works. However, this is almost never what you should actually do. This is a theoretical result, but it is not the practical way to solve a system of equations. Some other important properties is that for any non-singular matrix, the following statements are true. A has a unique inverse. A inverse itself is non-singular, and the inverse of the inverse is back to the original matrix A. A transpose is also non-singular. And furthermore, if B is non-singular, then A times B is non-singular, and the inverse of AB is given by B inverse A inverse. And lastly, the solution to AX equals B is unique. So that's where we're going to stop. Up next in the next video will be matrix and vector norms.